Now, we have discussed about the different elements that can be derived. So, either these elements is a fuzzy set or is a fuzzy rule or is a relation or proposition or some inferences, whatever it is there. Now, whatever the elements that is there, they expressed in the form of a fuzzy concept, right. But the idea is that we can understand instead of fuzzy rather the crisp. Whenever we have to use this fuzzy value, then they should be converted into the crisp value. So, in today actually we will discuss about how a fuzzy value can be converted to the crisp value. This discussion basically involves a lot of techniques to be discussed. So, we will take maybe 2 lectures to discuss the whole topics. So, first we can consider the first part of the discussion. So, we say the discussion diffusion techniques part 1, and so let us see how it is basically the concept of defuzzification. It is actually, as I told you, defuzzification means from a fuzzy value to a crisp value. Now, as an example I can say T high is a fuzzy set, the temperature is high representing, and this fuzzy set takes this form. So, our objective is that if this is a fuzzy set, then exactly what is the high temperature in the concept of crisp value. That means, what is the crisp value that implies high temperature. So, one way if I ask you, you can give that 50.09 is the high temperature, because it has the highest what is called the high value of the membership, degree of membership. But some people can say that okay, I can take neither very low value nor high value or the medium value, that means this one, Okay. So, there will be 2 value and then take the minimum or average of the 2 value. So, this one whatever it is there, or a middle value one also can be taken as the high temperature. Now, these are the basically guessing, and in let us see in fuzzy theory how such a crisp value can be calculated rather with more mathematical tuning. Another example, say suppose, so this is the one fuzzy set is given in the form of a graph. So, this basically describe a fuzzy set of with this continuous values of element x, then what is the crisp value? That means, whether crisp value is this one or this one, or it is this one, or it is somewhere this one. Okay. So, crisp value is this one or this one or this one, which one it is basically. So, let us see how the fuzzy mathematics fuzzy logic provides us a way to calculate the crisp value for such a element like a fuzzy set shown in the form of a graph. Now, another example. So, here also we have to obtain the crisp value. Here this example is more complex of course. So, idea is that these are the 2 rules is given, this is the rule, right. Then what is the output? If x is a, then y is c, and if x is b, then y is d. Then if these 2 rules are given, then for x equals to say some element x dash, that means if x dash is a, then y is c, and x dash is b, then y is d, then what is the final crisp conclusion from the 2 rules, that is fireable to x equals to x dash. So, this rule can be computed again using the defuzzification technique. The broad idea of the defuzzification technique is shown here. So, suppose this is the fuzzy set A defined over the same universe of discourse x, and this is the B defined over the universe of discourse x, and y is C, that means C fuzzy set, D fuzzy sets are defined by this one, and they are defined over the another universe of discourse y. Now, for some element x dash, right. So, this is the x dash. So, we want to calculate the rule strength, actually this is called the rule strength or the rule value. So, here basically if we see x dash is fireable with this membership value mu x dash here, and a mu mu b x dash is here. Okay. So, if we draw a line and then this one, so this basically if x is a, then y is c, basically have this strength up to this one. Okay. So, this one, if x dash is someone here, then it will go there, or above there it will go there, or it is here there. So, depending on the values of x dash, so the portion that will cover it is there. Now, this portion basically tell that what is the value of this rule. Likewise, if x dash is b, and then y is d. So, if we draw a line, then we intersect this portion. So, this basically rule strength for this. Now, taking the merging of the two, so that two rules have the value this shaded area. So, this is the shaded area basically is the fuzzy value given these two rule. Now, given this is the fuzzy value, then how we can obtain the Cripps value. So, this is the task, and we can solve this kind of problem using the concept of defuzzification technique. Now, so why defuzzification, or really it is very important or not, that is also important. So, as I told you, defuzzification requires because some application where it can take if the conclusion is available in the form of a Cripps value. For example, if you want to develop one what is called the AC controller, air conditioner controller. So, that controller basically will control depending on the temperature. So, the controller is designed like this. If temperature is high, then rotation is fast. Now, temperature is high for a particular temperature, say 40 degree, then rotation is fast, then means we have to go for fast rotation. Now, this value should pass to the controller in such a way that controller can understand a particular value only, that is this is the rotation, say 30 rotation per seconds. So, then it will calculate. So, that if this is fuzzy and this is fuzzy, then finally we should have what exactly the defuzzified value or Cripps value for this one. So, it is the usual okay, this is one simple example that I have placed here. So, that if something is fuzzily available, input or output whatever it is there, finally we need the Cripps value to be used for some final application. Now, so this is basically the model that is followed in fuzzy system design, as I told you here. So, basically this is the fuzzy system that we want to design. Now, fuzzy system takes the Cripps input and then Cripps output, because we can think only in the terms of Cripps value, and also we can conclude something if the Cripps value is known to us. So, we are habituated with the Cripps value rather than fuzzy value, but the fuzzy system will take only the fuzzy values. So, the first step is that the Cripps value should be converted to the fuzzy value. So, there is a fuzzified input. Then from the fuzzified input it will go to the inference mechanism. So, that means if this is the input and they are the fuzzy rule base, that means a set of rules. We have already discussed about how the rules can be stored in the form of a matrix. So, it is basically a set of matrix is given there. Now, there is a technique regarding the inference mechanism, we will learn about it later on, and if the fuzzy input is given to this inference mechanism will discuss about the fuzzy rule base, then we will obtain another fuzzy output. Now, this fuzzy output needs to be defuzzified, and then the defuzzified result can be passed to the outside of the fuzzy system as a Cripps output. So, basically is a fuzzifier and defuzzifier and then fuzzy rule base and inference mechanism. These are the four basic components or four basic tasks that is involved in order to develop a fuzzy system. Now, the fuzzifier, as you know, so the fuzzifier is basically a task of the fuzzy designer, fuzzy engineer, who basically can convert Cripps input to fuzzy input. So, it is basically in the form of a fuzzy system development. Fuzzy engineer has to give an idea how a Cripps input can be stored in the fuzzy form, and then these are the basically fuzzy rule based system, and then the inference mechanism can results the defuzzy. These are the basically different fuzzy operations related to the fuzzy sets, related to the fuzzy rules, fuzzy propositions, and then fuzzy implications, finally the different inferences can be obtained, and this inference, from the inferences we will be able to defuzzify it, so the crisp output. So, now we are discussing basically how the fuzzy elements, whether it is in the form of a set or it is in the form of a relation matrix, can be defuzzified, so that the crisp result can be obtained. So, let us see what the different techniques are available. So far the defuzzification technique is concerned. So far the defuzzification technique is concerned, many methods are known. We can broadly categorize the different methods. We have categorized as 4. The first method is called Lambda-cut method. The second method is weighted average method, and the next is maxima method, and finally the centroid methods. Now, these are the different methods. The way a fuzzy value can be converted to its corresponding to its crisp value. So, different methods has their own merits as well as own limitation. We will learn about it whenever we discuss the different methods one by one. Now, first we will discuss about the Lambda-cut method. Now, Lambda-cut method is a very popular method already known in the context of crisp theory, crisp algebra, that means in the context of set algebra or Boolean algebra. The same thing can be extended in the context of fuzzy theory. So, Lambda-cut method for fuzzy relation and Lambda-cut method for fuzzy set. Okay, so we will discuss about first the Lambda-cut method for fuzzy set and then Lambda-cut method for fuzzy relation. Now, let us first discuss about the Lambda-cut method for fuzzy sets, so that from a fuzzy set to crisp set can be obtained. So, idea it is, so in this method the fuzzy designer should choose one value, the value is called lambda, that is why the method is called Lambda-cut method. So, lambda value should be in the range 0 to 1. Now, so then the Lambda-cut method, it is basically, we have discussed when we discussed about the fuzzy terminology, that is basically A lambda is a alpha cut like is. So, it is A alpha, actually alpha is lambda here. So, A lambda, and A lambda is basically a crisp set which can be obtained, that it includes all the elements x such that mu A x is greater than or equals to lambda. That means, from the given fuzzy set we can find a crisp set, so that the elements whose membership value is greater than or equals to lambda. So, this is the value of lambda set, and so this is also depend on the A lambda. For the different values of lambda, definitely A lambda will be different. Now, so A lambda is also alternatively called alpha cut set, because we have discussed about the cut set of a fuzzy set. So, it is a alpha cut set. Now, let us see one example, so that we can discuss about this Lambda-cut method here. So, this example say, so A1 is a fuzzy set, and let us consider lambda is 0.6. So, it is A lambda, that is the Lambda-cut according to the value of lambda, this one. So, it will basically take all the elements whose membership value is greater than or equals to 0.6. So, this way x1 is qualified, this is not qualified, this is not qualified, this is not qualified. So, we can convert this fuzzy set into the, this is the crisp set, or more general form, the crisp set can be expressed as this one, because those are the 0, they should not be there, and those are the element 1, this one. So, A1, if this is the fuzzy set, and then if we follow certain value of lambda, then the crisp set can be obtained, and this is the crisp set. That means, if say temperature is high, this one, then the high temperature will be x1 temperature like this one. So, it is the example like this. Now, as a second example, so suppose this is another fuzzy set A2, and we take lambda equals to 0.2. That means, you will take those elements whose membership value is greater than or equals to 0.2. So, it is not qualified, this is qualified, this is also qualified, and this is also qualified. This means that the A2 given the fuzzy sets and lambda which is specified as 0.2, the crisp set that can be obtained, this is the crisp set. Now, we can say that, so Lambda-cut gives you a crisp set Cripps set can be a null or it can have one or more elements in the set. Now, in case of one or more element, they are basically all the equal answer as in the context of Cripps, that okay, if this is the fuzzy, then this is the Cripps value, either it is x 2, x 3 or x 4, or you can take the mean of the 3 values to conclude precisely that this is the Cripps result. So, it is the idea about the Lambda-cut method, and this is the in the context of fuzzy sets. Now, the same idea can be calculated for the other complex fuzzy forms. Here as an example, say suppose you have given two fuzzy sets P and Q with the membership value it is shown here in this table, then definitely we will be able to calculate these things with our previous knowledge. Now, if we have to calculate P union Q and lambda is 0.6. So, the idea is that we first obtain the fuzzy union of these two fuzzy sets P Q, and then for the resultant fuzzy sets we can apply 0.6, then we can obtain the result of this P union Q for this 0.6 lambda set. Similarly, this one and this one also can be calculated. So, idea can be extended to the complex formulation relating to two or more fuzzy sets as well. Now, we can again extend the same concept of Lambda-cut set to fuzzy relation or in a relation matrix. So, idea it is like this: a relation matrix, we know it is, suppose for an example a relation matrix is given here, it is take this form. Now, again a relation matrix, if the Lambda-cut for a fuzzy relation can be specified with respect to a specific value of lambda. I am giving here 4 examples. So, if lambda equals to 0, then how the Cripps relation can be obtained. So, if lambda equals to 0, that means we will take only those entries whose basically value greater than 0. So, that means in this case, if so this is R lambda, lambda equals to 0, and basically all entries are qualified. So, this is the Cripps relation matrix. Now, again say suppose 0.5 if we take, that means we can take only those entries whose value is greater than 0.5, greater than or equals to 0.5. So, this one, this one, this one, this one, this one and this one. So, this way these are the different value that is there in the Cripps relation. So, this is a fuzzy relation and these are the different Cripps relation. As you know, the fuzzy relation can have entries in between 0 and 1 both inclusive, whereas Cripps relation is basically has this one, and so it is okay. So, is a Cripps, so is a fuzzy. So, fuzzy to Cripps can be calculated using the Lambda-cut method like this one. Now, the same thing can be applied to other things also. Okay, there are some properties hold good. So, for the Lambda-cut set is there, this property okay needs to be understood right. So, basically this is the one property that if A union B and their Lambda-cut is taken, this is basically equivalent to take the Lambda-cut of A and Lambda-cut of B and taking their union. So, this is basically one rule also applicable. This rule also just it is for union, it is for intersection, and one thing is that A lambda their complement and then complement A lambda, they are not generally equal, but they are only equal for A equals to 0.5. And for any lambda which is less than alpha, alpha is another value in between 0 and 1, we can check, we can prove that A alpha is always a proper subset of A lambda if this inequality holds. So, these are the properties, it basically holds good. So, for the Lambda-cut technique is concerned. Similarly, for the relation, these are the properties also satisfied. This property is for union, and this is for intersection, and this is for the complements, and this is the subset of this relation. So, this is the Lambda-cut method in general, and we can conclude one thing regarding the Lambda-cut method is that Lambda-cut method converts a fuzzy set for a fuzzy relation into Cripps set or a Cripps relation. So, basically fuzzy set to fuzzy Cripps set or a fuzzy relation to Cripps relation. Now, before going to discuss the other technique, I will discuss about output of a fuzzy system, how basically the output of a fuzzy system can be concluded or can be calculated given many fuzzy elements, or more precisely we will discuss about many fuzzy rules are there. So, if more rules are given, then how we can conclude that what is the result is there. That means, for a given input, say suppose the n rules are applied. So, for a input R1 is also satisfied, R2 is also true, Rn is also true. So, n number of rules are true for a particular input, then what is the output? So, output is basically, so if it is a rule satisfied giving B1, B2, Bn, then output can be like this, that it is basically union of B1, B2, Bn, but not exactly the union, it is basically the rule strength related to x is 1, that B1. So, it is not the entire B1, but a part of the B1, x is A2, not the entire B2, but a part of the B2. So, basically fuzzily it is part of B1, part of B2, part of B1. So, it is a part of B1, part of B2, part of B1, and if we take the union of all these parts, then finally it will gives the total, what is called the parts, that all these rules basically signify for the output. Now, here is the idea about that how this kind of calculation is possible, and then their corresponding Cripps value. So, this idea can be mathematically better described, and I just discuss in terms of two rules. The same idea can be explained more than two rules as well. Now, here is an example, we can check it clearly. So, suppose two rules are given here, the two rules is if x is A1 then y is C1, and another rule is if x is A2 then y is C2. Now, for an input say x equals to some x dash, okay, we have to calculate what is the rule strength. Now, here you can see I just okay. So, graphically I can calculate it, or graphically I can display it. So, it is basically the fuzzy set A, and this is the fuzzy set B, and here the C1 and C2 other two fuzzy sets C1 and C2. Suppose they are defined over the same discourse x, and this the rule C1 C2 fuzzy set defined over the discourse y, and these are the graphical representation of their sets. Now, so if x equals to x1, that means it qualifies this one. If x equals to x2, then it fire both A and B, and if x equals to x3, it fires only set B, but not set A. Now, so the three different situations I have mentioned here. If for a given value only if x is A, then y is C, it is fired, but this B is not fired, only one. So, in that case, if we draw a line parallel to this, so as it is only related to C1, so this is the part of the set C1, that is basically the rule strength of this one. Now, again if x is 2, then it satisfies both part. So, if we consider this part, then this is the C, and if we take this part, then it is this one. So, the rule strength is basically the total part is this one. So, this is the basically the resultant fuzzy set. Now, the next is x3 is basically only this one, A does not satisfy, this means this rule does not fire, but this rule fire in this case, and then we can see this part, then it is basically this part. So, for this rule the rule strength will be this one, that means this is the fuzzy output. So, we have some idea about that for the given rule or set of rules, how the fuzzy output will be there. So, geometrically a fuzzy output is basically a geometrical shape, and this basically a portion like this portion or is a curve like. So, this is also a fuzzy set, I mean like how look like this. So, we have to obtain the Cripps value from these fuzzy sets like. Now, let us see how such a things can be extended in more general way. I can extend the same idea again here. So, as I told you, if x equals to x1, so this is the only part that is covered, that means if x is A, then y is C, the fuzzy output is this one is the fuzzy output in this sense. Now, if as another example, if x is 2, then the fuzzy output will be this one. So, this is the fuzzy description of the output. And the second case is if x equals to x 3, then this is the fuzzy output. Okay. So, this is the fuzzy output. Fine. So, we have discussed about the fuzzy defuzzification technique, and particularly we discuss in these topics the Lambda-cut method, and then how the output of a fuzzy system can be calculated. We will discuss the second part of the defuzzification technique, particularly if a different geometrical shape is given to us which represents a fuzzy output, how the crisp value can be calculated. That will be discussed from our next lecture. Thank you.